Hi, so welcome back. And on the last video, we finished um, on the topic 2.4.5, where I explain how you can representate a rigid body in a space. And we stop on the example 2.4, and now we will cover this example. So let's dive into it. So he says that for the following referential, which is represented for by this matrix, and some elements is missing, as you can see. And he asked for us to complete these elements that are missing on this representation matrix form of the referential. And to clarify this statement that I did, representation of referential in the matrix form. Which is what we are doing right here. And this statement can be illustrated right here. So let's copy this. Let me copy this and drag down a bit. Okay. Let me write again the statement representation matrix representation of a referential. And it's nice when you understand exactly what you are doing. So right here, just to remember, is the XYZ system of reference, and we can have another referential system that can be right based on this. So let's see right here, which is the one that we are covering this whole time, and AO reference system. And on the past video, we talk about the equations of restriction that we need to write when we are working with rigid bodies, because right here we have 12 elements. These elements not counting this scale factor, and actually a rigid body, it has only 6 degrees of freedom, so we need to write these equations of restriction. Okay, so let me rearrange. And I'm gonna copy this and paste right here. 6 equations of restriction for the rigid body and analysis. And also let's clarify this. This column is the representation of the position in the region of the referential. So if I'm not wrong, is this vector decomposed on the x, y, z coordinates, if I'm not wrong, because the book is not letting this clearly. Okay. And for solve this example, we need to go back, and if you are following on the last video, we saw that in order to write these equations of restriction, we need to consider this sentence of the referential of the axis, knowing the referential system that we are using and the axis that we are working on it. And what that means, the sentence are telling to us that those 3 vectors which form the system of reference, A and O, are orthogonal between them, and the length, this other statement, are saying to us that the length of each unit vector, which are those one, must be equal 1. And we're going to have the following equation, and um, I'm gonna be anticipate this for you. Why we are reading again the sentence that we saw on the last video. Exactly because of this. They are mutual orthogonal. That is this point, this dot, is not the operation of multiplication. Instead, is the scalar product, as we saw. So what does that means? Nx times Ox, Ny times Oy. We have this configuration right here, but this means the orthogonality that they make. Is that what this equation it has on this on his arm? And I cannot forget that is referenced to another referential. And can you see? It's what happens. And when we have a vector or a rigid body, we can rotate any position or rotation based on the system is what is happening. Okay, let me write the orders. It's 6 equations or 6 equations. And based on the second statement, the length of a vector, if you remember a vector, we can calculate his length taking but let's work already. These are vectors. A ON. Those are unit vectors of this reference system. And a vector can be calculated taking his square root. The square root of the sum of the components square of the components. And now eliminating the square root. And we will do the same for the other components, for the other unit vectors. Now for N and O. Okay, and he asked for us to find these missing elements. So let's solve these equations and substitute. We can substitute to follow to find these missing elements. Let me copy this representation of a referential in the matrix form. Because it's going to be useful right here. And this one too. So to rewrite these equations and solve them, we just need to substitute these values, the ones that we have, on these equations. And let's see what we're going to obtain. In x times ox, and ox, as you can see, is equal to 0. So let's substitute this right here. And ny, as you can see, is equal 0.707, and we just have to substitute right here. Times OY and NZ times OZ, which is equal 0. And we repeat this process for these other equations. Okay, so we are left with the following. And now this is being multiplied by 0. Right here 2, 0, 0. So let's do another simplification. So we are left with 0.707 times OY AY times OY is equal 0, and okay, now we just need to solve these equations, and let's start from the most obvious, which is this one. And let's start you need to pay attention on this. If you write that AY is equal 0 divided by OY, which is equal 0, then AY necessarily needs to be different from 0. And if you write that OY is equal AY divided, 0 divided by AY, which is equal 0, then OY necessarily needs to be different of 0. Okay, and we will work based on this combination. So that's our first equation. AY times OY, which is equal 0, will be OY will be equal 0. And necessarily AY necessarily needs to be different from 0. And now we can use this information to solve the other ones. This one now. Pretty obviously, right? Let's copy this and paste right below, right here. So now that we find OI, which is equal 0, then O squared Z is equal 1, and OZ is equal 1 when we take the square root. And if we solve all of these equations, we're going to obtain for nx the following. For nz 0, oy 0, oz equal 1, ax equal n, ay equal. Solving the 6 equations. So now let's write this matrix with the missed elements that we find right here. And as you can see, we will have two matrix because of these values of minus and plus signal. And now for the other signal. And with this, we finish the example, and he says that, as you can see, both of these matrix uh, satisfy all the requirements defined by the equations of restriction. And we also has another form to resolve this example or exercise. Instead of do the scalar product, use the product vector product, but this technique will not use. And with that being said, thank you.